Welcome to Lecture 11. In our previous session, we introduced the foundational concepts of objects and classes. Today, we will delve deeper into the core pillars of object-oriented programming that enable powerful code reuse and organization, inheritance, and polymorphism. We will also explore the related concept of encapsulation. These are not just academic terms. They are practical tools that allow you to build programs that are modular, extensible, and easier to maintain. Inheritance is a mechanism that allows you to define a new class based on an existing class. Alongside encapsulation, it is one of the fundamental cornerstones of object-oriented programming. The key relationship is between a superclass, also known as a base class or parent class, and a subclass, also called a derived class or child class. The subclass automatically inherits all public attributes and methods from its superclass. This means you can create a new class that is a specialized version of an existing one, reusing and building upon established functionality without rewriting it. When we speak of inheritance, we refer to the transfer of characteristics. In programming, this means all public attributes and methods defined in the parent class become part of the child class automatically. This promotes the do not repeat yourself principle, reducing redundancy and enhancing maintainability. Inheritance establishes an is-A relationship. If class B inherits from class A, we can say B is a type of A. This logical relationship is the cornerstone of building taxonomies in code, just as in biology, where we classify species into genera and families based on shared traits. This relationship allows us to think at different levels of abstraction. At a higher level, we define general behaviors. At lower levels, we specialize. This layered approach helps manage complexity by allowing us to focus on one level of detail at a time. Inheritance also facilitates polymorphism, which we will discuss later. When multiple classes share a common parent, they can be treated uniformly in certain contexts, while still exhibiting their own specific behaviors. Python supports various forms of inheritance, including single, multiple, and hierarchical. When these are combined, we refer to it as hybrid inheritance. This flexibility allows developers to model intricate relationships, though it requires careful design to avoid confusion in how classes relate to one another. The syntax for inheritance in Python is clear and minimal. After the class name, we place parentheses containing the name of the parent class. This declaration alone grants the child class access to everything the parent offers. The body of the child class then introduces new or modified features. To appreciate inheritance, consider a scenario without it. Suppose we have a person class with a name attribute and a method to display it. Now we need an employee class that also has a name and a display method plus additional work-related behavior. Without inheritance, we would duplicate the name and display code, a clear violation of good design principles. With inheritance, we define employee as a subclass of person. The employee class automatically receives the name, attribute, and display method. We only need to add what is new, the work behavior. This eliminates duplication, ensures consistency, and localizes changes. Python permits a class to inherit from more than one parent. This is multiple inheritance. For instance, a class could inherit from both an employee class and a student class, combining the capabilities of both. This is powerful but introduces complexity, particularly when parent classes have methods with the same name. Python resolves such conflicts using a defined method resolution order. A subclass can override methods inherited from its parent. This means providing a new implementation for a method with the same name. However, often we wish to extend the parent's behavior, not replace it entirely. For this, we use the super function to call the parent's version of the method, then add additional logic. Consider a person class with a general method. An employee subclass might override this method to include job-specific details. By using super, the employee's method can invoke the person's method to handle the common part, then proceed with its own specialization. When dealing with a hierarchy, we sometimes need to execute different code depending on the specific type of an object. The isInstance function allows us to check an object's class. We can then direct behavior accordingly. However, overuse of type checking can be a sign of poor design. Polymorphism often provides a cleaner solution. Let's consider a more extended example, a table class representing a physical table. A desk table subclass might add a method to calculate surface area. A computer table subclass of desk table might further adjust that calculation to account for monitor space. This chain of inheritance allows each level to build upon and refine the previous one. Here we see another hierarchical example, a school class with student subclasses. One student subclass may itself become a parent to another, more specialized class. This illustrates how inheritance can create complex, tree-like structures that mirror organizational or conceptual hierarchies. Polymorphism is a cornerstone principle in object-oriented programming. The term derived from Greek means many forms. In practice, it describes the ability of a single function, method, or operator to behave differently depending on the object or data type it is acting upon. This is not a separate feature, but a natural outcome of well-designed class hierarchies and interfaces. We encounter polymorphism daily, even in simple operations. Consider the plus operator. When used with integers, it performs arithmetic addition. When used with strings, it concatenates them. When used with lists, it merges them. The same operator symbol changes its meaning based on the type of its operands. This is a powerful form of abstraction, allowing us to express the idea of combining in a consistent way across different data types. Polymorphism extends to functions as well. Certain built-in Python functions are designed to accept arguments of various types and perform appropriate actions. This design makes our code more general and flexible, as the same function call can work correctly with different kinds of data. A classic example of function polymorphism is the len function. You can pass it a string, and it returns the number of characters. Pass it a list, and it returns the number of elements. Pass it a dictionary, and it returns the number of key-value pairs. Internally, len works by calling a special method named awklen that each of these object types defines. This consistent interface, despite different underlying implementations, is the essence of polymorphism. This ability to apply a single function to multiple data types simplifies our thinking. We don't need a separate count characters function for strings and a count elements function for lists. One function, len, serves a universal purpose, measuring size. This reduces the mental overhead and the number of functions we must remember, making our code cleaner and more intuitive. The real power lies in the interface. If you create a custom class, for example, a playlist class for managing songs, you can define your own len method inside it. Suddenly, your custom object also works seamlessly with the built-in len function. This is how polymorphism bridges built-in functionality and user-defined types, creating a unified and predictable programming environment. Polymorphism finds its most intentional use in class methods. Different classes can have methods with the same name. When we call that method, the correct version is selected automatically based on the object's actual class at runtime. This allows us to write code that processes objects generically, trusting each object to know how to perform its own specific actions. Consider two classes, cat and dog. Both might have methods named makeSound and info. For a cat, makeSound would print meow. For a dog, the same method call would print bark. We can write a loop that iterates over a list containing both cats and dogs and calls makeSound on each. The appropriate sound is produced for each animal without us needing to check its type explicitly in our code. This is polymorphism in action. This approach makes systems extensible. If we later add a bird class with its own makeOnSound method, our existing loop will continue to work without any modification. The new bird object will simply fit in and produce its sound. Polymorphism, therefore, is a key enabler of software that can grow and adapt over time without constant rewrites of core logic. Here is another illustrative example. Two unrelated classes, T1 and T2, both have a method called total. However, their internal implementations are completely different. One performs addition, the other calculates string length. When we call total on an object, the result depends entirely on which class the object belongs to. This demonstrates that polymorphism doesn't require an inheritance relationship. It simply requires a shared method name, allowing for duck typing, a philosophy central to Python. Duck typing is the idea that if it walks like a duck and quacks like a duck, then it is a duck. In code, this means we care more about an object's behavior, what methods it has, than its specific class. Polymorphism through duck typing allows for incredibly flexible and loosely coupled systems, where objects from different hierarchies can collaborate as long as they support the required methods.